Good evening, everyone. Um, okay, the topic that I'm going to present is the magnetic anisotropy. And first of all, we have some outline related to this topic in which we are going to discuss the introduction, some of the causes, and there are some of the types of the anisotropy in which we have the crystalline shape, stress and strain, and exchange anisotropy. And then we have some of the application related to this and some of the research trend that is going to discuss this topic. Okay, in introduction, basically we have a definition. Anisotropy is any kind of the behavior that is related to the direction. And when we talk about the magnetic anisotropy, so any kind of property of material which involve the magnetic moments or the magnetization under the influence of the external magnetic field. And because of this external magnetic field, the atoms or the magnetic moments, they are going to align themselves in such preferred orientation where it is easy to align them. So in here we have an illustration that indicates the easy axis and the hard axis. Basically, easy axis are the axis where the magnetization align very easily, and the hard axis basically where the magnetization aligned hardly because of the high energy requirements. And in easy axis we have the easy energy, or we can say the low energy requirements. And when we apply the external magnetic field, and when these magnetic moments align themselves with the easy axis, so it means that we have the high magnetic moment. And here we can see in this electric illustration where all the magnetic moments, they are not aligned, they are in the different directions. But because we have the zero magnetic external magnetic field, and we can see that the direction of the moments is also zero. But when we apply the external magnetic field, which we show here, so the magnetization is equal to the magnetization direction of the magnetization moment, and all of the moments, they are aligned in the direction of the external magnetic field. And we can see in this, it's like of the crystal structure. Basically, it's hematite, or we can say iron, where we have the sphere, and these spheres have certain moments, magnetic directions, and some are parallel and some are anti-parallel. And this illustration basically is explain the spin arrangement of a material. So we have certain causes of the magnetic anisotropy, in which we can say we have a crystal structure. Like the crystal structure, basically it differ your magnetic anisotropy if you have the cubic material. So where the easy axes are more multiples, and we have the more magnetic anisotropy as compared to the non-cubic materials, in which the hexagonal or orthorhombic, they are included. And spin orbit coupling, like when you have the atom have basically the nucleus, and surrounding the nucleus there is an electron. When it surrounds, so it will create a certain magnetic field, and because of this coupling we have a specific magnetic moments. The shape of the material, it also influences the magnetic anisotropy. The doping also, because when we are doping on any kind of the impurity into our materials, will create the defects, and these defects basically change the electronic properties and as well as the magnetic properties of our material. And the stress or strain, any physical stress on your material, on your crystal structure, it can influence your magnetic anisotropy. The first of the type that we will discuss is the crystalline anisotropy, in which it depends upon the basically anisotropy that arises due to the symmetry of the materials crystal structure, whether it's cubic or it's non-cubic. So here is a table where we can see that the cubic anisotropy will include the FCC or the BCC cubes. They have the high anisotropy as compared to the non-cubic symmetry, where anisotropy, where it's the lower as compared to the cubic. So because here we have the multiple axis, easy axis, as compared to the non-cubic anisotropy, and the examples are mostly iron or the nickel, and here the example are cobalt and the mostly rare earth element. So we have the energy expression to explain, to calculate the energy of the crystalline anisotropy. As we can see in this illustration, the first of all we have like a cubic, where we can see the easy axis are more as compared to the hard axis. But when we see here in the hexagonal, the only easy axis is in the center of this crystal, and the other hard axis. So the non-crystalline or the non-cubic anisotropy having the lower magnetic anisotropy. The next is the shape anisotropy. So it depends upon the shape of the material also. Like if you have the thin films of the small particles and they are mostly associated on the surface of the material, so it also influence the shape, also influence the anisotropy. Like here in the illustration, we can see when we have a material, or you can see a cube that is the height is more as compared to the width. So the magnetization or the magnetic moment is parallel and is more to the upward. And when you convert into the material that has a lower length as compared to the width, so the magnetic moment is different, and as compared to the small object, so the shape of the material, the shape of the crystal affect the anisotropy. We have the expression, we have the equation just that will where we can calculate the shape anisotropy energy, and it's depending on the shape. Like if you have cube, if you have the hexagonal, or if you have the different shapes of your crystal, it will create the different preferred orientation, so it affects your anisotropy. The stress anisotropy, it basically is due to the mechanical stress or the strain on your material. It is because of any kind of pressure, any kind of temperature, and these all are the mechanical stresses on your material. Like you can say the amorphous ribbon, when it will pass through the hot zone, so we are creating the stress on that material with the help of the heat. So we have the thermomechanical treatment, and it will change the anisotropy of your material. And we also have the expression to calculate the stress anisotropy. The exchange anisotropy, in which ferromagnetic layer and the antiferromagnetic layer, they align themselves to create the interface in between them. As we see, the ferromagnetic layer, all of the magnetic moments, they align parallel, and into the antiparallel, they are antiparallel, as you can see. So when they join, so they create an interface, and here it's a little mechanism, and coupling of this, it will create the anisotropy, and that will affect your material performance also. Here is the in this illustration, as you can see, when you apply when the magnetic field is zero, so your magnetic moments, they are not aligned. But as you increase the magnetic field, they align themselves, and the domains with aligned magnetic moments, they grow at the expense of poorly aligned ones. So as we are increasing the magnetic field, they are going to align themselves in the direction of the magnetic field. And also you can see that here the saturation is like when you are going to apply the magnetic field, they are going to saturate it and they align themselves in preferred direction. But when you are removing that magnetic fields, they are getting demagnetized, but unmagnetized state. So when you apply, they align themselves. But when you remove, the alignment stay. If the alignment stays, it means they are the permanent magnets, they are the strong magnets. But in the cases where the alignment doesn't stay, so they are going to demagnetize themselves, and we have this loop. It's called the hysteresis loop. And anisotropy is different in the hard magnetic materials and the soft magnetic materials. Basically, in the hard, we have the high coercitivity and high remanence as compared to the soft materials, where it's the low. As you can see, we have the high hysteresis loop as compared to the soft material, where is the low hysteresis loop. And in case of the hard material, we have usually permanent magnets, and in case of this, we have generators, motors, and these kind of things that involve the low hysteresis loop. And the examples are basically the neodymium magnets. They are the strongly commercially available magnet. And we have some soft magnetic materials in which iron, cobalt, and nickel, these materials are involved. And we have some of the application related to the magnetic anisotropy. Basically, these is used in the data storage devices, in the hard disk, or the MRAM and the spintronics. And basically, most of these applications are involved in the biomedical applications or the navigation, and the permanent magnets also. So these are some of the applications related to the magnetic anisotropy, and we have some of the references and some of the work that involve a lot of information about this topic. And thank you so much.